We have introduced the concept of expected value or mean, which tells us the average value of a random variable. We will now introduce another quantity, the variance, which quantifies the spread of the distribution of a random variable. So consider a random variable with a given PMF, for example, like the PMF shown in this diagram. And consider another random variable that happens to have the same mean, but its distribution is more spread out. So both random variables have the same mean, which we denote by mu, and which in this picture it would be somewhere around here. However, the second PMF, the blue PMF, has typical outcomes that tend to have a larger distance from the mean. By distance from the mean, what we mean is that if the result of the random variable, its numerical value, happens to be, let's say, for example, this one, then this quantity here is x minus mu is the distance from the mean. How far away the outcome of the random variable happens to be from the mean of that random variable. Of course, the distance from the mean is a random quantity. It is a random variable. Its value is determined once we know the outcome of the experiment and the value of the random variable. What can we say about the distance from the mean? Let us calculate its average or expected value. The expected value of the distance from the mean, which is this quantity, using linearity of expectations, is equal to the expected value of x minus the constant mu, but the expected value is by definition equal to mu, and so we obtain 0. So we see that the average value of the distance from the mean is always 0, and so it is uninformative. What we really want is the average absolute value of the distance from the mean, or something with this flavor. Mathematically, it turns out that the average of the squared distance from the mean is a better behaved mathematical object. And this is the quantity that we will consider. It has a name. It is called the variance, and it is defined as the expected value of the squared distance from the mean. The first thing to note is that the variance is always non-negative. This is because it is the expected value of non-negative quantities. How exactly do we compute the variance? The squared distance from the mean is really a function of the random variable x. So it is a function of the form g of x, where g is a particular function defined this way. So we can use the expected value rule applied to this particular function g, and we obtain the following. So what we have to do is to go over all numerical values of the random variable x. For each one, calculate its squared distance from the mean and weigh that quantity according to the corresponding probability of that particular numerical value. One final comment. The variance is a bit hard to interpret because it is in the wrong units. If capital X corresponds to meters, then the variance has units of meters squared. A more intuitive quantity is the square root of the variance, which is called the standard deviation. It has the same units as the random variable and captures the width of the distribution. Let us now take a quick look at some of the properties of the variance. We know that expectations have a linearity property. Is this the case for the variance as well? Not quite. Instead, we have this relation for the variance of a linear function of a random variable. Let us see why it is true. We use the shorthand notation mu for the expected value of x. We will proceed one step at a time and first consider what happens to the variance if we add a constant to a random variable. So let y be x plus some constant b, and let us define nu to be the expected value of y, which using linearity of expectations is the expected value of x plus b. Let us now calculate the variance. By definition, the variance of y is the expected value of the distance squared of y from its mean. Now we substitute, because in this case y is equal to x plus b, whereas the mean nu is mu plus b. And now we notice that this b cancels with that b, and we are left with the expected value of x minus mu squared, which is just the variance of x. So this proves this relation for the case where a is equal to 1. The variance of x plus b is equal to the variance of x. So we see that when we add a constant to a random variable, the variance remains unchanged. Intuitively, adding a constant just moves the entire PMF right or left by some amount, but without changing its shape, and so the spread of this PMF remains unchanged. Let us know what happens if we multiply a random variable by a constant. Let again nu be the expected value of y, and so in this case by linearity this is equal to a times the expected value of x, so it is a times mu. We calculate the variance once more using the definition and substituting in the place of y what y is in this case, it's ax, and subtracting the mean of y, which is a mu squared. We take out a factor of a squared, and then we use linearity of expectations to note that this is a squared times expected value of x minus mu squared, which is a squared times the variance of x. So this establishes this formula for the case where b equals 0. Putting together these two facts, if we multiply a random variable by a, the variance gets multiplied by a squared. And if we add a constant, the variance doesn't change, and this establishes this particular fact. As an example, the variance of, let's say, 3 minus 4x is going to be equal to minus 4 squared times the variance of x, which is 16 times the variance of x. Finally, let me mention an alternative way of computing variances, which is often a bit quicker. We have this useful formula here. We will see later a few examples of how it is used, but for now let me just show why it is true. We have, by definition, that the variance of x is the expected value of x minus mu squared. Now, let us rewrite what is inside the expectation by just expanding this square, which is 2 minus mu x plus mu squared. Using linearity of expectations, this is broken down into expected value of x squared minus the expected value of 2 times mu x, but mu is a constant, so we can take it outside the expected value, and we're left with 2 mu expected value of x plus mu squared. But remember that mu is just the same as the expected value of x. So what we have here is twice the expected value of x squared plus the expected value of x squared, and that leaves us just a minus the expected value of x squared. So we will now move in the next segment into a few examples of variance calculations. In this segment, we will go through the calculation of the variances of some familiar random variables, starting with the simplest one that we know, which is the Bernoulli random variable. So let x take values 0 or 1, and it takes a value of 1 with probability p. We have already calculated the expected value of x, and we know that it is equal to p. Let us now compute its variance. One way of proceeding is to use the definition and then the expected value rule. So if we now apply the expected value rule, we need a summation over all possible values of x. There are two values, x equal to 1 or x equal to 0. The contribution when x is equal to 1 is 1 minus the expected value, which is p squared, and the value of 1 is taken with probability p. There's another contribution to this sum when little x is equal to 0, and that contribution is going to be 0 minus p, all of this squared, times the probability of a 0, which is 1 minus p. And now we carry out some algebra. We expand the square here, 1 minus 2p plus p squared, and after we multiply with this factor of p, we obtain p minus 2p squared plus p to the third power. And then from here we have a factor of p squared times 1 p squared minus times minus p, that gives us a minus p cube. Then we notice that this term cancels out with that term. P squared minus 2p squared leaves us with p minus p squared, and we factor this as p times 1 minus p. An alternative calculation uses the formula that we provided a little earlier. Let's see how this will go. We have the following observation. The random variable x squared and the random variable x, they are one and the same. When x is 0, x squared is also 0. When x is 1, x squared is also 1. So as random variables, these two random variables are equal in the case where x is a Bernoulli. So what we have here is just the expected value of x minus the expected value of x squared to the second power, and this is p minus p squared, which is the same answer as we got before, p times 1 minus p. And we see that the calculations and the algebra involved using this formula were a little simpler than they were before. Now, the form of the variance of the Bernoulli random variable has an interesting dependence on p. It's instructive to plot it as a function of p. So this is a plot of the variance of the Bernoulli as a function of p, as p ranges between 0 and 1. P times 1 minus p is a parabola, and it's a parabola that is 0 when p is either 0 or 1, and it has this particular shape, and the peak of this parabola occurs when p is equal to 1/2, in which case the variance is 1/4. In some sense, the variance is a measure of the amount of uncertainty in a random variable, a measure of the amount of randomness. A coin is most random if it is fair, that is, when p is equal to 1/2, and in this case, the variance confirms this intuition. The variance of a coin flip is biggest if that coin is fair. On the other hand, in the extreme cases where p equals 0, so the coin always results in tails, or if p equals to 1, so that the coin always results in heads, in those cases we do not have any randomness, and the variance correspondingly is equal to 0. Let us now calculate the variance of a uniform random variable. Let us start with a simple case where the range of the uniform random variable starts at 0 and extends up to some n, so there is a total of n plus 1 possible values, each one of them having the same probability 1 over n plus 1. We calculate the variance using the alternative formula. And let us start with the first term. What is it? We use the expected value rule, and we argue that with probability 1 over n plus 1, the random variable x squared takes the value 0 squared. With the same probability, it takes the value 1 squared. With the same probability, it takes the value 2 squared, and so on, all the way up to n squared. And then there's the next term. The expected value of the uniform is the midpoint of the distribution by symmetry, so it's n over 2, and we take the square of that. Now, to make progress here, we need to evaluate this sum. Fortunately, this has been done by others, and it turns out to be equal to 1 over 6 n times n plus 1 times 2n plus 1. This formula can be proved by induction, but we will just take it for granted. Using this formula, and after a little bit of simple algebra, and after we simplify, we obtain a final answer which is of the form 1 over 12 n times n plus 2. How about the variance of a more general uniform random variable? So suppose we have a uniform random variable whose range is from A to B. How is this PMF related to the one that we already studied? First, let us assume that n is chosen so that it is equal to b minus a. So in that case, the difference between the last and the first value of the random variable is the same as the difference between the last and the first possible value in this PMF. So both PMFs have the same number of terms. They have exactly the same shape. The only difference is that the second PMF is shifted away from 0 and it starts at A instead of starting at 0. Now, what does shifting a PMF correspond to? It essentially amounts to taking a random variable, let's say with this PMF, and adding a constant to that random variable. So if the original random variable takes the value of 0, the new random variable takes the value of a. If the original takes a value of 1, this new random variable takes the value of a plus 1, and so on. So this shifted PMF is the PMF associated to a random variable equal to the original random variable plus a constant. But we know that adding a constant does not change the variance. Therefore, the variance of this PMF is going to be the same as the variance of the original PMF as long as we make the correspondence that n is equal to b minus a. So doing this substitution in the formula that we derived earlier, we obtain 1 over 12 b minus a times b minus a plus 2. We now move to a new topic, conditioning. Every probabilistic concept or probabilistic fact has a conditional counterpart. As we have seen before, we can start with a probabilistic model and some initial probabilities, but then, if we are told that a certain event has occurred, we can revise our model and consider conditional probabilities that take into account the available information. But as a consequence, the probabilities associated with any given random variable will also have to be revised. So a PMF will have to be changed to a conditional PMF. Let us see what is involved. Consider a random variable x with some given PMF, whose values of course sum to 1, as must be true for any valid PMF. We are then told that a certain event A has occurred. In that case, the event that x is equal to little x will now have a conditional probability of this form. We will use this notation here to denote the conditional probability that the random variable takes the value little x. Notice that the subscripts are used to indicate what we're talking about. In this case, we're talking about the random variable x in a model where event A is known to have occurred. Of course, for this conditional probability to be well defined, we will have to assume that the probability of A is positive. This conditional PMF is like an ordinary PMF, except that it applies to a new or revised conditional model. As such, its entries must also sum to 1. Now, the random variable x has a certain mean, expected value, which is defined the usual way. In the conditional model, the random variable x will also have a mean. It is called the conditional mean or the conditional expectation, and it is defined the same way as in the original case, except that now the calculation involves the conditional probabilities or the conditional PMF. Finally, as we discussed some time ago, a conditional probability model is just another probability model, except that it applies to a new situation. So any fact about probability models, any theorem that we derive, must remain true in the conditional model as well. As an example, the expected value rule will have to remain true in the conditional model, except that, of course, in the conditional model we will have to use the conditional probabilities instead of the original probabilities. So to summarize, conditional models and conditional PMFs are just like ordinary models and ordinary PMFs, except that probabilities are replaced throughout by conditional probabilities. Let us now look at an example. Consider a random variable, which in this case is uniform, takes values from 1 up to 4, so each one of the possible values has probability 1 over 4. For this random variable, we can calculate the expected value, which by symmetry is going to be the midpoint, so it is equal to 2.5. We can also calculate the variance, and here we can apply the formula that we have derived earlier, 1/2 times b minus a times b minus a plus 2. And in this case, it's 1 over 12 times b minus a is 4 minus 1, which is 3. And the next term is 5. And after we simplify, this is 5 over 4. Suppose that now somebody tells us that event A has occurred, where event A is that the random variable x takes values in the range 2, 3, 4. What happens now? What is the conditional PMF? In the conditional model, we're told that the value of 1 did not occur, so this probability is going to be 0. The other three values are still possible. What are their conditional probabilities? Well, these three values had equal probabilities in the original model, so they should have equal probabilities in the conditional model as well. And in order for probabilities to sum to 1, of course, these probabilities will have to be 1/3. So this is the conditional PMF of our random variable, given this new or additional information about the outcome. The expected value of the random variable x in the conditional universe, that is, the conditional expectation, is just the ordinary expectation but applied to the conditional model. In this conditional model, by symmetry, the expected value will have to be 3, the midpoint of the distribution, and we can also calculate the conditional variance. This is a notation that we have not yet defined, but at this point it should be self-explanatory. It is just the variance of x, but calculated in a conditional model using conditional probabilities. We can calculate this variance using once more the formula for the variance of a uniform distribution, but we can also do it directly. So the variance is the expected value of the squared distance from the mean. So with probability 1/3, our random variable will take a value of 4, which is 1 unit apart from the mean, or more explicitly, we have this term. With probability 1/3, our random variable takes a value of 3, and with probability 1/3, our random variable takes the value of 2. This term is 0. This is 1 times 1/3. From here we get another 1 times 1/3. So adding up, we obtain that the variance is 2/3. Notice that the variance in the conditional model is smaller than the variance that we had in the original model, and this makes sense. In the conditional model, there is less uncertainty than there used to be in the original model, and this translates into a reduction in the variance. To conclude, there is nothing really different when we deal with conditional PMFs, conditional expectations, and conditional variances. They are just like the ordinary PMFs, expectations, and variances, except that we have to use the conditional probabilities throughout instead of the original probabilities. An important reason why conditional probabilities are very useful is that they allow us to divide and conquer. They allow us to split complicated probability models into simpler submodels that we can then analyze one at a time. Let me remind you of the total probability theorem that has this particular flavor. We divide our sample space into 3 disjoint events, A1, A2, and A3, and these events form a partition of the sample space, that is, they exhaust all possibilities. They correspond to 3 alternative scenarios, one of which is going to occur. And then we may be interested in a certain event B. That event B may occur under either scenario, and the total probability theorem tells us that we can calculate the probability of event B by considering the probability that it occurs under any given scenario and weigh those probabilities according to the probabilities of the different scenarios. Now let us bring random variables into the picture. Let us fix a particular value, little x, and let the event B be the event that our random variable takes on this particular value. Let us now translate the total probability theorem to this situation. First, the picture will look slightly different. Our event B has been replaced by the particular event that we are now considering. Now, what is this probability? The probability that event B occurs, having fixed a particular choice of little x, is the value of the PMF at that particular x. How about this probability here? This is the probability that the random variable capital X takes on the value little x, that's what a PMF is, but in the conditional universe. So we're dealing with the conditional PMF, and so on with the other terms. So this equation here is just the usual total probability theorem, but translated into PMF notation. Now, this version of the total probability theorem, of course, is true for all values of little x. This means that we can now multiply both sides of this equation by x and then sum over all possible choices of x. we recognize that here we have the expected value of the random variable x. Now we do the same thing to the right-hand side. We multiply by x and then we sum over all possible values of x. This is going to be the first term, and then we will have similar terms. Now, what do we have here? This expression is just the conditional expectation of the random variable x under the scenario that event A1 has occurred. So what we have established is this particular formula, which is called the total expectation theorem. It tells us that the expected value of a random variable can be calculated by considering different scenarios, finding the expected value under each of the possible scenarios, and weigh the scenarios according to their respective probabilities. The picture is like this. Under each scenario, the random variable x has a certain conditional expectation. We take all these into account, we weigh them according to their corresponding probabilities, and we add them up to find the expected value of x. So we can divide and conquer. We can replace a possibly complicated calculation of an expected value by hopefully simpler calculations under each one of possible scenarios. Let me illustrate the idea by a simple example. Let us consider this PMF and let us try to calculate the expected value of the associated random variable. One way to divide and conquer is to define an event A1, which is that our random variable takes values in this set, and another event A2, which is that our random variable takes values in that set. Let us now apply the total expectation theorem. Let us calculate all the terms that are required. First, we find the probabilities of the different scenarios. The probability of event A1 is 1/9 plus 1/9 plus 1/9, which is 1/3. And the probability of event A2 is 2/9 plus 2/9 plus 2/9, which adds up to 2/3. How about conditional expectations? In a universe where event A1 has occurred, only these three values are possible. They had equal probabilities, so in the conditional model they will also have equal probabilities, so we will have a uniform distribution over the set 0, 1, 2. By symmetry, the expected value is going to be in the middle, so this expected value is equal to 1. And by a similar argument, the expected value of x under the second scenario is going to be the midpoint of this range, which is equal to 7. And now we can apply the total probability theorem and write that the expected value of x is equal to the probability of the first scenario times the expected value under the first scenario plus the probability of the second scenario times the expected value under the second scenario. In this case, by breaking down the problem in these two sub-cases, the calculations that were required were somewhat simpler than if you were to proceed directly. Of course, this is a rather simple example, but as we go on with this course, we will apply the total probability theorem in much more interesting and complicated situations. We will now work with a geometric random variable and put to use our understanding of conditional PMFs and conditional expectations. Remember that a geometric random variable corresponds to the number of independent coin tosses until the first head occurs, and here P is a parameter that describes the coin. It is the probability of heads at each coin toss. We have already seen the formula for the geometric PMF and the corresponding plot. We will now add one very important property, which is usually called memorylessness. Ultimately, this property has to do with the fact that independent coin tosses do not have any memory. Past coin tosses do not affect future coin tosses. So, consider a coin tossing experiment with independent tosses, and let x be the number of tosses until the first heads. And x is geometric with parameter p. Suppose that you show up a little after the experiment has started, And you are told that there was so far just one coin toss, and that this coin toss resulted in tails. Now you have to take over and carry out the remaining tosses until heads are observed. What should your model be about the future? Well, you will be making independent coin tosses until the first heads. So the number of such tosses will be a random variable which is geometric with parameter p. So this duration, as far as you are concerned, is geometric with parameter p. Therefore, the number of remaining coin tosses, starting from here, given that the first toss was tails, has the same geometric distribution as the original random variable x. This is the memorylessness property. Now, since x is the total number of coin tosses, and since your coin tosses were all of them except for the first one, the random variable that you are concerned with is x minus 1. And so the geometric distribution that you are seeing here is the conditional distribution of x minus 1, given that the first toss resulted in tails, which is the same as the event that x is strictly larger than 1. So the statement that we have been making is the following in more mathematical language, that conditioned on x being larger than 1, the random variable x minus 1, which is the remaining number of coin tosses, has a geometric distribution with parameter p. Let us now give a more precise mathematical argument, but first for a special case. Let us look at the conditional probabilities for the random variable x minus 1 and calculate, for example, the conditional probability that x minus 1 is equal to 3, given that x is larger than 1, which is the same as saying that the first toss resulted in tails. Now, the first toss resulted in tails. This is the probability that you will need 3 more tosses until you observe heads. Needing 3 more tosses until you observe heads is the event that you had tails in the second toss, tails in the third toss, and heads in the fourth toss. And all that is conditioned on the first toss having resulted in tails. However, the different coin tosses are independent. So the conditional probabilities, given the event that the first toss was tails, should be the same as the unconditional probabilities. The first toss does not change our beliefs about the probabilities associated with the remaining tosses. Now, this unconditional probability is easy to calculate. It is 1 minus p squared, because we have 2 tails in a row, times p. Now we observe that this quantity here is the probability that a geometric random variable takes the value of 3. Here, what have we calculated? We have calculated the PMF of the random variable x minus 1 in a conditional universe where x is larger than 1, and we evaluated it for a value of 3. The probability that our random variable x minus 1 takes the value of 3. So what we have shown is that this conditional PMF is the same as the unconditional PMF. Now, there is nothing special about the number 3. You can generalize this argument and establish that the conditional probability of x minus 1, given that x is strictly larger than 1 for any particular k, is the same as the corresponding probability for the random variable x, which is the one given by the geometric PMF. Finally, there is nothing special about the value of 1 that we're using here. In fact, we can generalize and argue as follows. Suppose that I tell you that x is strictly larger than n. That is, the first n tosses resulted in tails. Once more, these past tosses were wasted but have no effect on the future, so the conditional PMF of the remaining number of tosses should be again the same. Therefore, the statement we're making is that this geometric PMF will also be the PMF of x minus n, given that x is strictly larger than n, and this will be true no matter what argument we plug in into the PMF. We will now exploit the memorylessness property of the geometric PMF and use it together with the total expectation theorem to calculate the mean or expectation of the geometric PMF. If we wanted to calculate the expected value of a geometric using the definition of the expectation, we would have to calculate this infinite sum here, which is quite difficult. Instead, we're going to use a certain trick. The trick is the following: to break down the expected value calculation into two different scenarios. Under one scenario, we obtain heads in the first toss, and in that case, the random variable x, the number of tosses until the first head, is equal to 1, and this scenario occurs with probability p. And we have another scenario with probability 1 minus p, where we obtain tails in the first toss, and in that case, our random variable is strictly larger than 1. Now, the expected value of x consists of two pieces. We have a first toss, no matter what, and then we have the number of remaining tosses, which is x minus 1. So this is true by linearity of expectations. Now, the expected value of x minus 1 consists of two pieces using the total expectation theorem. The probability of the first scenario times the expected value of x minus 1 given that x is equal to 1 plus 1 minus p, the probability of the second scenario, times the expected value of x minus 1 given that x is bigger than 1. Now, this term here is 0. Why? If I tell you that x is equal to 1, then you are certain that x minus 1 is equal to 0, so this term gives a 0 contribution. How about the next term? We have a 1 minus p here, times this expected value. Now, this random variable conditioned on this event has the same distribution as an ordinary unconditioned geometric random variable. So this expectation here must be the same as the expectation of an ordinary unconditioned geometric random variable. And this gives us an equality. Both sides involve the expected value of x, but we can solve this equation for the expected value, and we obtain the end result that the expected value is 1 over p. By the way, this answer makes intuitive sense. If p is small, this means that the odds of seeing heads is small. Then in that case, we need to wait longer and longer until we see heads for the first time. Setting aside the specific form of the answer that we found, what we have just done actually illustrates that fairly difficult calculations can become very simple if one breaks down a model or a problem in a clever way. This is going to be a recurrent theme throughout this class. By this point, we have discussed pretty much everything that is to be said about individual discrete random variables. Now, let us move to the case where we're dealing with multiple discrete random variables simultaneously and talk about their distribution. As we will see, their distribution is characterized by a so-called joint PMF. So suppose that we have a probabilistic model, and on that model we have defined two random variables, x and y, and that we have available their individual PMFs. These PMFs tell us about one random variable at a time. This tells us about x, this tells us about y, but they do not give us any information about how the two random variables are related to each other. For example, if you wish to answer this question, whether the numerical values that the two random variables happen to be equal and what is the probability of that event, you will not be able to answer this question if you only know the two individual PMFs. In order to be able to answer a question of this type, we will need information that tells us what values of x tend to occur together with what values of y, and this information is captured in the so-called joint PMF. So the joint PMF is nothing but a piece of notation for an object that's familiar. This is the probability that when we carry out the experiment, we happen to see random variable x take on a value little x and simultaneously see that random variable y takes on a value little y. This quantity we indicated with this notation. The letter little p stands for a PMF. The subscripts tell us which random variables we're talking about. And finally, this is a function of two arguments. Depending on what pair x, y we're interested in, we're going to get a different numerical value for this probability. As an example of a joint PMF in which the two random variables take values in a finite set, we might be given a table of this form. Using this table, we can answer questions such as the following. What is the probability that the random variables x and y simultaneously take the values, let us say, 1 and 3? Then we look up in this table and we identify that it's this probability. X takes the value of 1 and y takes the value of 3. And according to this table, the answer would be 2 over 20. Now, something to notice about joint PMFs. When you add over all possible pairs x and y, this exhausts all the possibilities. And therefore, these probabilities should add to 1. In terms of this table, all the entries that we have here should add to 1. Now, once we have in our hands the joint PMF, we can use it to find the individual PMFs of the random variables x and y. And these individual PMFs are called the marginal PMFs. How do we find them? Well, the joint PMF tells us everything there is to be known about the two random variables, so it should contain enough information for us to answer any kind of question. So, for example, if we wish to find the probability that the random variable x takes the value of 4, we look at all possible outcomes in which x is equal to 4 and add the probabilities of these outcomes. So in this case, it would be 1 over 20 plus 2 over 20. So what we're doing is that if we're interested in a specific value of x, the probability that x takes on a specific value, we consider all possible pairs associated with that fixed x. That is, we're considering one column of the PMF, and we're adding the corresponding probabilities. So to find this entry here, let's say px of 3, what we need is to add these terms on that column. Similarly, we can find the PMF of the random variable y. So, for example, the probability that the random variable y takes on a value of, let's say, 2 can be found as follows. You look at the probabilities of all pairs associated with this specific y and you add over the x's. So we fix y to have a value of 2 and we add over all pairs in this row. So in this example, it would be 1 over 20 plus 3 over 20 plus 1 over 20. Finally, notice that we are able to answer the question that got us motivated in the first place. To find the probability that the two random variables take equal values, we look at all the outcomes for which the two random variables indeed take the same numerical values, and we see that it is this event in this diagram, and the probability of that event is going to be 2 over 20. So, in general, once we have available the joint PMF of two random variables, we will be able to answer any questions regarding probabilities of events that have to do with these two random variables. How about more than two random variables? It's just a matter of notation. For example, we can define the joint PMF of three random variables, and you can use the same idea for the joint PMF, let's say, of 5 or 10 or n random variables. Let's just look at the notation for 3. There is a well-defined probability that when we carry out the experiment, x, y, and z as random variables take on certain specific values. So we look at the probability of that particular triple and we indicate that probability with this notation. Once more, the subscripts tell us which random variables we're talking about, and the PMF, of course, is going to be a function of this triple, little x, little y, little z, because each triple in general should have a different probability. Of course, probabilities must always add to 1. So when we consider all triples and we add their corresponding probabilities, we should get 1. And finally, once we have the joint PMF, we can again recover the marginal PMF. For example, to find the probability that a random variable takes on a specific value little x, we consider all possible triples in which the random variable indeed takes that value little x, and then we sum over all the possible y's and z's that could go together with this particular x. In the same spirit, to find the probability that these two random variables take on two specific values, we consider all the possible z's that could go together with this xy pair. So this way we're ranging over all outcomes in which x and y take on these specific values, but z is free to take any value. And so we consider all those possible values of z and sum the corresponding probabilities. Finally, we can talk about functions of multiple random variables. Suppose that we have two random variables, x and y, and that we define a function of them. So this function is, of course, a random variable, and we can find the PMF of this random variable if we know the joint PMF of x and y. So the PMF, which is the probability that the random variable takes on a specific numerical value, that's the probability that the function of x and y takes on a specific numerical value. And we can find this probability by adding the probabilities of all xy pairs which xy pairs, those xy pairs for which the value of z would be equal to this particular number little z that we care about. So we collect essentially all possible outcomes that make this event to happen, and we add the probabilities of all those outcomes. Finally, similarly to the case where we have a single random variable and the function of it, we now can talk about expected values of functions of two random variables, and there is an expected value rule that parallels the expected value rule that we had developed for the case of a function of this form. The form that the expected value rule takes is similar and it's quite natural. The interpretation is as follows. With this probability, a specific xy pair will occur, and when that occurs, the value of our random variable is a certain number. And the combination of these two terms gives us a contribution to the expected value. Now we consider all possible xy pairs that may occur, and we sum over all these xy pairs. Let us now revisit the subject of expectations and develop an important linearity property for the case where we're dealing with multiple random variables. We already have a linearity property. If we have a linear function of a single random variable, then expectations behave in a linear fashion. But now, if we have multiple random variables, we have this additional property. The expected value of the sum of two random variables is equal to the sum of their expectations. Let us go through the derivation of this very important fact, because it is a nice exercise in applying the expected value rule and also manipulating PMFs and joint PMFs. We're dealing with the expected value of a function of two random variables, which function, if we write it this way, we are dealing with the function g, which is just the sum of its two entries. So now we can continue with the application of the expected value rule, and we obtain the sum over all possible xy pairs. Here we need to write g of xy, but in our case the function we're dealing with is just x plus y, and then we weigh according to the entries of the joint PMF. So this is just an application of the expected value rule to this particular function. Now let us take this sum and break it into two pieces, one involving only the x term and another piece involving only the y term. Now, if we look at this double summation, look at the inner sum. It's a sum over y's. While we're adding over y's, the value of x remains fixed. So x is a constant as far as this sum is concerned. So x can be pulled outside this summation. Let us just continue with this term, the first one, and see that a simplification happens. This quantity here is the sum of the probabilities of the different y's that can go together with a particular x, so it is just equal to the probability of that particular x. It's the marginal PMF. If we carry out a similar step for the second term, we will obtain the sum over y's. It's just a symmetrical argument. And at this point, we recognize that what we have in front of us is just the expected value of x, this is the first term, plus the expected value of y. So this completes the derivation of this important linearity property. Of course, we proved the linearity property for the case of the sum of two random variables, but you can proceed in a similar way or maybe use induction, and one can easily establish by following the same kind of argument that we have a linearity property when we add any finite number of random variables. The expected value of a sum is the sum of the expected values. Just for a little bit of practice, if, for example, we're dealing with this expression, the expected value of that expression would be the expected value of 2x plus the expected value of 3y minus the expected value of z. And then, using the linearity property for linear functions of a single random variable, we can pull the constants out of the expectations, and this would be twice the expected value of x plus 3 times the expected value of y minus the expected value of z. What we will do next is to use the linearity property of expectations to solve a problem that would otherwise be quite difficult. We will use the linearity property to find the mean of a binomial random variable. Let x be a binomial random variable with parameters n and p, and we can interpret x as the number of successes in n independent trials, where each one of the trials has a probability p of resulting in a success. Well, we know the PMF of a binomial, and we can use the definition of expectation to obtain this expression. This is just the PMF of the binomial, and therefore what we have here is the usual definition of the expected value. Now, if you look at this sum, it appears quite formidable, and it would be quite hard to evaluate it. Instead, we're going to use a very useful trick. We will employ what we have called indicator variables. So let us define a random variable xi, which is a 1 if the ith trial is a success and 0 otherwise. Now, if we want to count successes, what we want to count is how many of the xi's are equal to 1. So if we add the xi's, this will have a contribution of 1 from each one of the successes. So when you add them up, you obtain the total number of successes. So we have expressed a random variable as a sum of much simpler random variables. So at this point, we can now use linearity of expectations to write that the expected value of x will be the expected value of x1 plus all the way to the expected value of xn. Now, what is the expected value of x1? It is a Bernoulli random variable that takes the value 1 with probability p and takes the value of 0 with probability 1 minus p. The expected value of this random variable is p. And similarly for each one of these terms in the summation. And so the final end result is equal to n times p. This answer, of course, makes also intuitive sense. If we have p equal to 1/2, and we toss a coin 100 times, the expected number or the average number of heads we expect to see will be 1/2 times 100, which is 50. The higher p is, the more successes we expect to see, and of course, if we double n, we expect to see twice as many successes. So this is an illustration of the power of breaking up problems into simpler pieces that are easier to analyze, and linearity of expectations is one more tool that we have in our hands for breaking up perhaps complicated random variables into simpler ones and then analyzing them separately.